So to start with, we'll look at what is called as a baseband data transmission. Okay, so in the simplest words, if you want to define what is a baseband signal, the baseband signal is something which exists naturally. Okay, for example, speech, right? We can generate speech, it's a baseband signal. Okay, and something which exists naturally. Any other example you can give? Music, right? The visual, whatever we see, right? That's this thing, and the light waves, etc. Those are the baseband signals. Okay, but one very important feature is that the normally existing baseband signals are analog in nature, right? So we know that in order for efficient communication, right, you have to use the digital version of the, you have to convert the analog signal into digital. This is our fundamental requirement. Why? Yes, we know that. I assume that we have already studied that in the previous chapters. Okay, right? There are many reasons why you need to convert analog into digital. Okay, fine. Now, let us assume that I convert this into the digital, right? Digital basically stands for, right? You try to represent the time axis as well as the frequency, time axis as well as the amplitude axis, you convert into the, you try to quantize, right? So basically digital represents, right? Have you heard the word quantization? Yes. So, right, what you are trying to do here is the y and x axis, both the y and x axis get quantized. In the sense, you cannot have any value you want. Like you will predefine, like, okay, after 0, I have 1, then 2, then 3. It's not as necessary these values like 0, 0 0.5, 1, 1.5, something like that. You quantize. Okay, this is the fundamental meaning of converting analog into digital. Right? Let's quickly look at the idea now. So if I say this is my analog signal, right? Something like this, right? This is, maybe I have can write y of t versus time, right? If you try to convert this into digital, right? This is how it's going to look like. So I told I have to quantize, right? Which says that, okay, what I do, I'll try to copy this, say, copy the same signal from this, and then I convert that into digital. Okay, right. For that reason, so let me say this is my signal, and let me say I is this. Okay, this was my original signal, but I cannot have all the values required like this. Okay, so that means I can have only the values which are located at specific locations. What I do, since I have a graph over here, I'll define only the values which are like this at every 2 instants. So after 2 seconds, whatever I get, only those values I try to take it. Okay, so this value, then this value. Okay, then I have this value, then I can have this value like this. Okay, then one. Okay, I think I copied only one location. Maybe I have to move two at a time. 1 2, then 1 2, then 1 2 over here, and 1 2 possibly. Okay, so like this. Now you see, if you want to look at the digital version of the signal which we have, right, considered so far, this is going to look like this. It's only the discrete locations. So whatever discrete values we have written, only those values can take, like this. You see, this is like this. So only the red lines what you see is the digital version of the analog signal. Okay, so it's like this. Then it moves till here. It comes down to a new value. It moves like this, this, and this, and this. So anyway, we can connect if required for our understanding purpose. Okay, let's assume. So you see that the y-axis has been discretized. It can take only these values. No value, intermediate values are acceptable. Similarly, the horizontal axis also has the discrete values, right? Every fixed interval of time, you are looking at what is the amplitude. That amplitude you are going to hold. Anyway, so this is what already has been studied. And I am converting the baseband analog signal into the equivalent discrete signals, wherein I can see a lot of pulses coming into picture. Where are the pulses? See, this is a pulse. This is the next pulse, right? This is the third pulse. I'm trying to represent everything in the form of pulses, right? All the way, right? This is our fundamental idea that, okay, if I'm trying to convert a analog into digital, first step I get pulses. So pulses are the fundamental representation of the analog signal, which is a baseband signal, in its equivalent digital format. I hope that is clear. This is n versus, maybe I can write y of n. Maybe we studied something like that in uh, whatever, in signals and systems, right? But actually, you are trying to sample this at a specific interval of time, TB, 2 TB, 3 TB, where TB is this duration. Okay, one duration is the TB, bit duration or symbol duration you can call. So generally, we don't write y of n in communication. You always write this is y of TB, okay, which is the digital equivalent. At every TB, whatever is the value, you are going to hold that value and you are trying to generate the pulses. Okay, right. So this is what is our fundamental idea, which we are going to start this chapter with. Okay, so I have an analog signal. I already converted that into digital equivalent signal in the form of pulses. I have pulses. Right. So now you see, right, what happens, what are the characteristics of these pulses is what we are going to investigate in this particular chapter. What are the properties, right? So whenever you have a signal with you, definitely signals properties are not clearly visible in time domain, but as soon as you move into the frequency domain, you get more properties, right? You get to see more properties. So what is the tool that takes you from time domain to frequency domain? It's a Fourier representation, right? So I have maybe x of t is my signal, right? Take any Fourier representation. I'll write maybe Fourier transform, assuming that the signal is not periodic. Okay, so if you have x of t, you have x of f representing, or x of omega. Okay, fine. Now, so as soon as you move into the frequency domain, right, you will be able to visualize what are the first thing. What is the first thing the x of f gives you? It actually tells you many things, right? Uh, Anything which you know, you please tell, right? As soon as I have a x of t, I took its Fourier representation, right? I get a plot. From that plot of x of f, what do you come to? Will it give any information related to the signal, that is x of t? So t was a time variable. So you are able to visualize at what time, what is the amplitude. That is x of t. When you move it to x of f, right? What is the domain of the signal? Domain is frequency, right? So at what frequency, what is the amplitude, you are able to see that, correct? So which means you get the details of the frequency, right? Or frequency contents of the signal. You come to know that whether the signal has 20 hertz, 50 hertz, 80 hertz, 120 hertz present in that or not. Okay, if the amplitude is high at a frequency, you can say that, okay, that frequency is present. If it is not, you say that that frequency is absent. Okay, that frequency is not present. Okay, so this is the first idea. By doing some changes in your x of f, you get to know one very important aspect, that is called as a power. How much power is present in each of the frequency? Have you heard any term which relates power to frequency? Absolutely perfect. So that is called as the PSD, right? The x of f actually gives, you have to do slight modification, right? X of f is my fundamental equation, right? But I slightly modify the x of f to get the PSD, power spectral density of your wave. Now, why this is important? This is one very important aspect in communication because, right, everything is related to frequency. What frequency you send, what you frequency you receive on the receiver side is very important. Okay, because of that, because of the PSD part, we will always come to know how much power I need to put at a particular frequency so that your signal reaches 100 kilometers. Because your target, maybe I want to send a signal 100 kilometers or 200 kilometers or something. Okay, this is what happens in the calculation of maybe the digital transmission. How much power I should give at a particular for a particular frequency so that my, maybe assume that I am a digital radio channel. All right, fine. So I want to cover an area of say 250 kilometers around my radio station. So I am transmitting at maybe say 2000 megahertz. Fine, possible, right? And I want to cover this much area, right? Means, right, I have to put at least this much energy for at least this much power, sorry, not energy, to the frequency, right, at which you transmit, right? This is the requirement. So power spectral density, spectrum means we know that it is a frequency plot. How much power is present at what frequency is very important. Okay, so that gives, this is very important because this gives you the PSD, right? This is a measure of the power present in any frequency content of the signal, because x of f is the frequency content. If you want to know how much power in each of the frequency that is present in the signal, PSD is the one tool which helps you to find out that. Okay, right. So this is going to help you to find and calculate the power requirements at various frequencies of the signal. Okay, fine. This is the fundamental. I'll just go ahead. Right, now I'll come back. Anyway, I moved into the frequency domain. I know what I'm going to do. Right, but on the time domain, I have to come back now because over here, I simply draw some pulses. Are they will there be any other types of pulses used? Because of some requirement, you may not be able to use the exact pulses which I have written over here, right? Maybe some conditions. What conditions are there? We'll see later. So first we'll start with the types of pulses that you can use in the communication. Okay, so what are the, we'll still we'll restrict our discussion to the time domain for the time being, right? So that is called as, what are the various types of pulses you use? It is coming under a specific type called as the discrete pulse amplitude modulation, discrete PAM. So pulse amplitude modulation, in short, it is called as a PAM. Right. So simply a digital data, which is a sequence of binary digits. So we know that, right? We try to represent in this most simplified form, the digital signals will have only two levels. Now you see here we have n levels, right? Maybe this is a level, this is another level, and so on, right? I have multiple levels, but let us start our discussion with a digital signal which has only two levels. What do you call it? It's called as a binary, right? Only two levels, right? So let's start with the you can have multiple levels for sure. You can have four levels in digital signals, right? Which will be represented as 00, 01, 10, 11, right? You can have next 8 levels, 16 levels, and so on. Okay, but for the time being, we'll keep the discussion as simple as possible. Okay, so let us assume that we have the binary sequence. All right, binary sequence contains only either zeros or ones. So when you have simply zeros or ones, right, you can have only two levels. Correct? Fine. Okay. Now, any electrical signal, let's come back to the fundamental concept that, and again, I'm taking these concepts from your previous chapters, right? Though I want to transmit audio, video, or whatever, music, right? Anything you want to transmit, ultimately, there will be some transducer which converts your baseband signal into electric signal first. Okay, take audio speech right now. I am talking, right? My mic will convert my audio into the electrical signal first. So fundamentally I'm trying to transmit a electric signal somehow. Okay, so there is a electric signal which is again analog, right? Inside my computer gets converted into, right, the required digital format. What levels, how many levels, it's decided already. So software takes care of that. Absolutely fine, no issues. Fine. So let's move further. Now that whatever analog signal, right, let us assume that is converted into two levels, right? So our electric signal got converted into two levels. Now any so two levels, 0 and 1, so level low or high, etc., right? You can call it by any name, that's fine, even true or false, no issues. Okay, now we have two levels. How many ways you can try to represent the two levels are what is covered under the discrete PAM. Okay, you can give different waveforms corresponding to your requirement. Okay, so how they are going to be decided, we will look at the power spectrum, etc. Later on we will be able to decide that which one to be choose. Okay, which one you can choose, we'll see later. Okay, so basically, right, the discrete PAM signals are nothing but the waveforms for the purpose of transmission over the required channel. So I'll quickly write one point here. The PAM signals show the various waveforms available for the transmission. Right, for the transmission, I actually have to continue here, but I don't want to write transmission of your binary sequence. Okay, anyway, already you are in the digital domain, right? Everything is digital. For I repeat, for the simplicity we considered only two levels. Okay, right, let's take an example first. Let's take a sequence. Let's try to represent that sequence in the various possible formats which are considered as the discrete PAM signals. Okay, which is nothing but what are the types of the pulses, right, that are available for you to transmit. Okay, so let's take a simple signal for time. Okay, so this is okay, let's consider the digital data now. So let sequence to be transmitted is 1 0 0 1 1 0 1. Okay, so this is how many bits? We have 7 bits to be transmitted. All right. Now, let us try to convert this into the various possible types. Okay, right. So let me start with the plot. So this is the time axis. Say t is equal to 0 for us. Now, right. The first, okay. First, let me write the allowed time. So this is the sequence which I want to send. This is 1, then 1 0 0 1 1 0 1. Okay, now the fundamental requirement of our uh, transmission in digital domain is that you have to decide what is the duration of each of the bit, right? So I'm going to send one for this much duration. You fix it, right? For the complete communication, it has to be fixed. Like I select maybe 2 milliseconds. In 2 milliseconds, I'll send one. The next 2 milliseconds, I send zero, right? Next millisecond, 2 milliseconds, I'm sending zero, next zero, and so on, right? So this has to be decided. So in order to plot this, I'll also take care of the same thing. I'll assume some bit duration. So when you draw, we are expecting that to remain same. Okay, so maybe if this is my this thing, I'll okay. Let me draw another way. I'm not able to copy. Okay, so assume that this gap should remain a constant value. Now it see that this is bigger, this is smaller, but actually it is expected that it has to remain same. All right. Okay. So like that, I'll divide whole the complete graph into right the equal spaces like this. Okay. Right. So we need one more here. This is the next bit duration TB and one more. Okay. Next bit duration and the last. Okay. Right. Now just to differentiate data, I'll draw one line. Okay, so this corresponds to just simply the data. Okay, now the first format which we are going to plot here is called as the, I'll write the name in red color just for your reference. This is NRZ, non-return to zero. NRZ stands for non-return to zero, and the name is called as unipolar. It's a category of pulse. Okay, specific type of pulse. Anyway, let me draw that. Okay, this is my x-axis, right? This is the time. Now you see, one is represented as high and zero is represented as low. There are only two values, maybe a one for this and a zero for this. Okay, zero is zero. In the sense, whenever you want to send one, you actually send one. So that's the meaning. You see here, now I'll change the color for my graph. For the waveform, you see this is one. Whenever you want to send one, you send a high pulse. Okay, and whenever you want to send, this is the simplest form of the pulse. Okay, I want to send zero, simply don't send anything. You see, this is on zero. Okay, I'll change. I have two ones now, so maintain the same high level for the two for 2-bit duration because I wanted to send one more, right? Then you see I want to send a zero. So that means you come down and you, this is the low, okay? And last should be high. Okay, this is the very, very simplified, very simple format. Okay, This is called as non-NRZ, non-return to zero, in the sense why it is called non-return to zero, because during the transmission of one, in its within its uh, bit duration, it is not coming to zero, which indicates that there are some waveforms in which they will come to zero. That's just an indication. Okay, but not in this. In this NRZ, in any way, waveform, wherever you see NRZ, that indicates that in whenever the signal is high, it is never coming to zero during the pulse duration. That is first thing. Second thing, there is the name says that it is unipolar, right? Polarity is only one, indicating that either there is what zero has no polarity. Polarity is high, only one polarity. Okay, that also indicates that there are some waveforms, pulse shapes, wherein you can have two or more polarities, right? That's what is the indication. Fine, this is the simplest one. Let's move further. So the next wave that we are going to waveform next we are going to see is a slight variation of this unipolar NRZ. It is called as RZ, return to zero. This is going to come to zero. This is RZ unipolar, right? As the name suggests, I'm expecting the waveform to come to zero somewhere in the middle. Okay, we'll see that. This is the time axis, right? Now you see it has to come to zero because RZ, and it can have only one polarity, that is high. Okay, let me define this is 1, this is a low. Okay, high and low, 1 and 0. But you see the waveform has to come to zero whenever it is high, right? It is high. So the characteristic is that I'll change the color for uh, clarity. Okay, now you see this. So my first waveform is high. It starts with 1, but you see this, its very fundamental characteristic is that at somewhere in the midpoint it comes down to 0. It is high for only half the duration, then it comes down to 0. Whenever it is 0, no problem, it remains 0. So that means I have to draw ones. You see, when there are continuous ones, we see the difference. This is at the middle, it comes down to 0. Okay, one more 1, so it comes still here and it comes down to 0. Now you see return to 0 comes into picture. So whenever it is 1, it is high, it retains its high value only half the duration, correct? And then it comes down to 0. So whenever the signal is 0, no problem, directly connect the low values directly till here. Okay, so it is 0, no problem. Only when it is high, it comes down. So I have to connect this till here, and I also have to connect this till here, right? So this is the difference. It has only one polarity for high, that is 1. That's the first point. And it is returned to 0, indicating that, right, it comes down to 0 whenever after halfway through, whenever the symbol is 1. So remember, right, the two. Next, we'll move further. Right. Now, the next one that we are going to plot is this is a pulse shaping technique which is called as return to zero RZ, and this is polar. Okay, this is RZ polar. Right. Okay, so this is how it's going to look like. Let me right. So RZ polar has two polarities, right? Okay, I just have to extend this now. Let me just extend. All right. Now in RZ polar, so polar says there will be two polarities. Okay. So one polarity I'm going to call this is high, maybe one. There is a zero, and equivalently on the other side, I'm requiring another polarity for minus one. Maybe this could be all in terms of the voltage levels. This can be like something like uh, minus 2 volts, 0 volts, and 2 volts. Possible. Okay, but we represent 0, 1, minus 1. Okay, now it means it is written to 0 and it has to have two polarities. Okay, let me just write the signal which we are writing once again. So that means I'm trying to plot a 1 here, 1, 0, 0, 1, 1, 0, 1. Okay, so whenever it is 1, right, it has to have higher polarity. Whenever it is 0, it has to maintain minus 1 as its polarity. That's the fundamental idea behind return to 0. Okay, and polar. Right, let's try to draw this. So this is 1, so this has to start at plus 1, but it has, okay, I'll change the color. Uh, okay, now it has to start at plus 1, it has to go halfway through, and it should come down to 0. Right, but you see the next bit you are sending is 0, which means it has to start from minus 1, and halfway through it has to come down back to 0. Okay, so 1 is plus 1, 0 is minus 1, but halfway after the half of the bit duration you need to come back to 0 is the characteristic of this particular uh, pulse shaping format. Okay, very important to remember, because I think one question will definitely come. They give a bit sequence and they will ask you to plot any of the I think we have 7 various options. Okay, it will, it's a definite question. This is 1, 1, then we have a 0, then we have 1. Okay, you see that there is a difference among the various types of pulses that we consider. Okay, right. This is all right. So that is RZ polar, right? Next format that we are going to plot is NRZ polar. It's non-return to 0, but polar. As the polar suggests, that you have to have two different polarities, right? This is another easiest format to remember as well as to plot. Okay, so we need to have two different polarities. I'll call this is 1, and maybe this is the minus 1. So whenever 1, you have to send 1 completely, because non-return to 0, right? So very simple. Let's do this. So this is completely 1. Okay, and I have 0, means I have to send directly, I need to send minus 1. So for the complete duration, send minus 1. Okay, then I have 1, so that means I need to send like this. Then I have a 0, so this is my waveform, and then I have 1. Okay, that's all, very straightforward, right? That is NRZ polar. Okay, then we have bipolar techniques, right, to follow, right? So that means the next waveform will be NRZ. This is bipolar, right? So we have the two polarities, and The two polarities will be used only when you have consecutive ones. Okay, so just try to differentiate the bipolar techniques with the polar techniques, because polar will also have two polarities, but specifically bipolar has a characteristic which uses the second polarity only when you have two continuous ones. Okay, 0 is a 0, but when I have two continuous ones coming into picture, only then I use the second polarity. Okay, let's look at the example. Okay, so I'll write my data once again. This is 1 0 0 1 1 0 1. Okay, so this is first polarity for 1, and this is another polarity -1. Right, so you see, first I have 1. That's a first one, so no issues. Directly you can draw. 1 is a 1. 1 is high. Okay, immediately after that you have to check whether you have a second one. No. So that means, right, you are going to simply plot 0 itself. 0 is a 0, no issue, right? Next, after this I get another one. So as soon as you get a first one, now it is a first one, it's not a continuous one, so it will be, right, once again 1. Okay, but now you see I got a second one. So as soon as you get another one over here, right, you need to shift to the other polarity which you have, that is -1. Okay, that's the difference. Other than that, everything is very similar to the NRZ polar format. So there is a 0, 0 is a 0. Next I'm getting my it's not a consecutive one, it's a first one I'm getting in this thing. So I can simply plot it as this. All right, so you see this is the NRZ, non-return to zero bipolar format. So definitely that leads to the another question, will I have a RZ format, right? So the answer is yes. We are going to plot the next one, which is return to zero, RZ and bipolar, right? So RZ bipolar will have the same NRZ bipolar technique, but there has to be an what you call a return to zero concept. Sorry, the return to zero concept also coming into picture. Okay, right, so we'll plot that now. Okay, so to plot the return to zero bipolar format, so as the name suggests, there has to be two polarities. So let's keep one as one of them +1, that will be a 0, and we'll keep this as the lowest possible polarity, that is -1. Okay, but since, right, you have a return to zero, right, uh, again, so 0 will remain as 0, so no problem with the 0 plotting, remember. So 0 will remain at a 0 level, so this is a 0. Is it 0 first number? Sorry, first value is 1, right? My mistake, redraw that, sorry. Okay, so I'll just write down the numbers here, otherwise I miss. So 1 0 0 1 1 0 1. Okay, so first one is +1, but it has to come to 0 after halfway, right? That's the return to 0 concept, right? So it comes to 0 at this point. Fine, no problem. Then I have zeros. So zeros will remain 0. You can simply plot zeros all the way through till here. Next, I get a 1. So as soon as you get a 1, you plot like this. Is it okay? Fine. But you see now I have a second one coming into picture. So sorry, all the bipolar techniques use the other polarity whenever you have a consecutive one. So this is how it will be plotted. Then I have a 0 following this, so it's going to be like this. Next, I have another 1 coming, so that 1 will be, okay. Then I can definitely draw the remaining. I hope this is clear, right? The return to 0 bipolar, right? And the one more very important plot or pulse waveform technique is called as the Manchester. This is also called, in some of the textbooks, authors call it as a biphase. All right, so don't get confused. All right, so biphase, plot the biphase waveform or plot the what you call Manchester state, what are same. Okay, all right. Now, again, in case of the Manchester, the there is what you call there are two levels. Okay, so level is +1 and level is -1, and there is no level 0. Okay, right? No level 0 will be used. This 0 what we have at the center, right, is never going to be used. Okay, and always, right, you, whether you are sending 1 or 0, half of your PB you send either +1 or -1. Remaining half you send the other one. In a sense, if you are sending 1 for the half, remaining half you will send the -1. So how do you decide that? This is the logic. So anyway, I'll write the this is once again 1 0 0 1 1 0 1. So you see here for 1, right, for sending 1, right, you send +1 for the half of the duration as the requirement, remaining half should be the -1, right? So I sent 1 till here, so I have to send the remaining half as the -1. This is the waveform. Okay. Now the biphase says that whenever 0 comes, you do the reverse. In the sense, first half you send -1, then remaining half you send the +1. Are you okay? So that means I have to send, see, just like this. Half of the waveform send -1 now, remaining half send this. Okay. This is repeated throughout. That's all. I just have to remember this logic. So I'm once again getting a 0, right? So which means I have to repeat the same thing. So first half I'm going to send the -1, then I'll shift to the +1. Okay, repeat that. So this goes till here. Now I see that my next one is 1, so I have to send like this, right? That's right. So next, once again, I have +1, so I'm going to send it in this format. Next, I can see that I have a 0. So first half should be negative, then the remaining half should be positive, right? Repeat that. So +1, then you send like this. So that is called as the Manchester or by phase uh, pulse technique under PAM. Okay, overall we have uh, so many waveforms that can be used under the PAM, right? So It means I had an analog signal, say speech. I converted into an electric signal which I want to transmit. Right now, because of the advantages, we can definitely convert that into the digital format. Digital format includes pulses. Fine. Now, out of these pulses, right, which one you are going to use? Because my signal is something like whatever I say I am talking now, right? This gets converted into pulse, but out of these many pulses, which pulse you are going to choose, right? There has to be some criteria, correct? Right? There has to be some criteria. Can you guess any of them based on what criterion you may have to choose one of them? Sorry, you are not audible. Can you repeat? Levels in the case anyway. So for the representation purpose, whatever levels we have used here, when it comes to the practical transmission, right? Let's say that you are designing a transmitter. The levels get converted into what is called as voltage. Okay, level is a voltage over there, right? Though you say that, okay, I have a digital circuit, I'm trying to send zeros and ones, right? Zero, zero is a zero NAND gate or NOR gate, whatever. Zero, zero is one, etc. When we say, when it comes to the actual implementation of the on the chip, it becomes 3.3 volts and 0.5 volts. You see the difference, right? So one becomes 3.3 volts, the zero becomes zero point 0.5 volts, right? So actually the level refers to the voltage in the practical case. Okay, yeah, please go ahead. How you are relating the voltages to your answer? Yeah. No, it's correct. Actually, you are close to the answer. Expect that. That's why I'm giving you some time to think over it. So already I introduced one concept of the use. This is x of t. Assume this is x of t. What happens when you take x of f, right? You get the frequency. You know that frequency spectrum can be used to calculate the spectral density. Maybe you can relate something, right? You already know. That's why I introduced the word PSD earlier, right? So, so it tells what frequency has how much power. So voltages are directly related to power, correct? In some sense, right? Right, maybe, right, maybe your circuit, right, the whatever the transmitter which you are going to design, right, you want to restrict the maximum power to some limit, right? I don't want to spend more than say 10 watts of power for transmission, let us say. Okay, very simple small transmitter, let's say. If you want to restrict your transmitting power less than 10 watts, maybe only those circuits, those waveforms which are high for half of your duration are suitable for that, right? You see the idea, right? I don't choose those pulses which actually are which exist completely during the time during your bit duration, like this. You see, I don't prefer this because they need more power, right? They have more power. So maybe you will select one which has only, which is on, because high, whenever I'm sending level high, 1 or -1, your circuit is on. Circuit is on means it is wasting power, correct? Yeah, so you don't choose any of the waveform which makes your circuit on for the complete duration. Instead of that, choose something which is active or which is on only for half of the duration. Maybe this one. You see, it's half. Whenever zero, it is completely zero. When you are not sending anything, whenever it is one, you are sending high for half the duration. Okay, fine. Your 10-watt transmitter which you are going to design is suitable maybe just for 10 meters. Okay, now I don't want that. I want to go for a 2 kilowatt transmitter, very huge, right? Very big antenna, very thin, this thing. So for that, I can never use this because it's not going to give you the 2 kilowatts of power at all, at any case, right? So you have to choose something, maybe this suits you because it is on for both positive and negative, right? In the sense, sorry, both for plus and minus, sorry, 0 and 1, sorry, please correct. Both for zeros and ones, my circuit is on, which means that might give you a 2 kilowatts power in some case. Okay, so now we are getting something, right? So on what basis? There are many other things, right, which is related to the uh, what you call the channel, right, over which you transmit, right? For example, I'll tell you one more thing because I don't want to start the next topic now itself because it will be half. But to cover the next 5 minutes, I'll tell you one more very interesting topic. Okay, again, it's going to come once again later in this chapter. But now let's see what is the other parameter which helps you to choose what is the shape of the pulse. Okay, now let us say I want to communicate for 100 kilometers, right? I'm, let us say I'm using wired communication. I have a very sophisticated wire from my location to the other location. Through the wire, I have to send the pulses. Okay. Anyway, everything is digital now, so there is no question of sending a or transmitting analog. So let us try to understand what happens when I try to send pulse through a very properly defined channel like wire. Okay, right, let me say I have two pulses defined, right? Let me try to send the pulses like, no, sorry, let me send simply two pulses, that's all. Okay, my intention is to send only two pulses. This is pulse number one, and very close to that, after its a bit duration or the symbol duration, I'm sending it's another pulse. Okay, two pulses, that's all. This is my signal which I'm transmitting, right? Let me assume that I have chosen a proper pulse according to my power requirement. I already have done some calculation and I have chosen this pulse. Okay, this pulse coding technique, right? So maybe it is simplest 101 possible. Okay, right. Now what happens as the distance is more and your waveform is traveling through the channel, that is a wire, right? Maybe I'll write, I wanted to communicate, say, as I told, 100 kilometers. Maybe just after 10 kilometers, what's going to happen? You see now, right? So I had the pulse defined something like this. So this was the highest value. I'll just draw dotted lines indicating this was the highest value which I sent. But you see, after 10, you may get something like this, right? You see, the because of the properties of the channel, obviously. It's nothing, no problem with your transmitter, no problem with the energy or the power you gave to the pulse. It is a property of the channel. Channel is a dispersive medium most of the time, which actually, right, takes some amount of energy, maybe because your conductor is a resistor. Resistor is a lossy component. We already studied in circuits, right? It loses the power. Energy, whatever energy you give to the resistor, it loses in the form of heat, right? Same thing, it, yeah, attenuation is also another version of talking about the same thing. Perfect, right? So because of that, I get like this. This is fine. Maybe this is after just 10 kilometers. You see what happens after maybe 25 kilometers. I'll change the color. Okay, so maybe after 25 kilometers, it becomes something like this. Now onwards, you have some problem, right? So maybe your detector, maybe I'll go to 100 kilometers this thing. So I'll change this to completely new color, maybe black. So after, say, right, 100 kilometers, what you get is this. Okay. Now the problem comes in the detection side. Whenever this signal is given to the detector may have a threshold to compare. Say the threshold is 50%. If it is more than that, it is 1. If it is less than that, it is 0. Let us say. Now you see, your signal is not at all crossing the threshold. Correct? So everything will be detected as 000 only. So you lose your complete information. Right? So this concept is called as symbols affecting other symbols, because right, if at all the threshold is very less, let's say the threshold is like this. What happens, this is detected as 1, I actually sent a 0, original symbol is 101, my 0 is also converted into 1, right? Maybe threshold is very less, means that's a problem. Anyway, there is a whole different concept to study how to design the transmitters, receivers, etc., right? But anyway, let's try to keep it as simple as possible now, right? So this concept, one symbol entering into the energy space of the other symbol, because your second symbol was 0, but the 0 was detected as 1 here. You see, if this is the lowest threshold is selected, this point will be a 1 on the receiver side, right? Which is a mistake, error, right? So you see, one symbol entering into the space of the other is called as inter-symbol interference. In order to avoid this, also you need to select a proper pulse, right? Pulse has to be properly selected so that even after communicating this much distance, okay, there will be attenuation, but your symbol should not enter into the region of your next symbol. Somehow you have to restrict that. So this is another very important parameter. In addition to this, I'll quickly finish. There is a transmission bandwidth. We have a complete idea about what is bandwidth. It is a total space available in terms of frequencies, right, which can be used for the transmission, right? So each of the rectangular pulse you use has a different frequency. It has, so the pulse, I'll directly go back to the diagram we wrote. So every pulse we have used here has different frequencies on the frequency. When you take the Fourier transform of every pulse and see NRZ's frequency, the Fourier transform of NRZ unipolar is completely different from RZ unipolar, completely different from RZ polar, completely different from this. So you see that means depending upon what frequencies are available for you to transmit, you will select this. So that was the third parameter. Again, you have what? Okay, the fourth parameter is, what if there is an error, right? Will you ask someone to send the message once again, or you will correct that somehow? So there is a concept called as detection of error and the correction, right? So which is more suitable for your communication protocol that you are using, right? According to that also you can choose the different shapes. Okay, then one more ultimate thing is efficiency, right? How much hours, how much power I give and how much power is received, there is a power efficiency coming to picture, right? Based on all of them, you can choose which waveform to be selected.